First of all, we take a common Avogadro old cigarette lighter and we pop it onto our already turred balance. Go to 0, pop it on there, make a note of the mass. I make that 11.28 G. This helps to have some patience because we have to take our 100 cm cubed cylinder, perfectly filled to the top, pop it underneath the surface of the liquid, and hey presto, no air bubbles. We have a complete column of water. I've never done this before. Taken a gas lighter and popped it into some water underneath the inverted measuring cylinder. If you can just come in a little bit, my lovely helping technician here. What's important to notice is that the beaker is full enough with water to get to round about 90 to 100. I can drop that down a little bit to about, let's put it at 90, because what we're going to do is when we've evacuated the water, or we've filled it with the butane gas, we need to make sure the level of this beaker here is the same as the level of the liquid within the column here in the cylinder. Okay, we've now adjusted the cylinder to 90. I put my hand in, so that's changed the level of the liquid. We're now going to evacuate the last 10 cm cubed. I can see that here. And then if we look closely at our cylinder, then both levels of the liquid in the cylinder and in the vessel in which it is contained are at the same level. That's critically important for our calculation, as you will see shortly. We are ready to take the final mass of the butane lighter. I recommend you dry it at least just using a paper towel. One of the errors in this, which we'll be looking at shortly, is inside. It's really hard to get rid of any water. Once we've done our best, maybe you could dry it overnight in a desiccator to reduce the error of that one. We take the new mass, and as you can see, the new mass is 11.05 G. Welcome back to my channel. This document will be appended as a bit.ly underneath the YouTube as usual. There is the full method. If you want to replicate it, steal away, may it serve you well. Let's have a look at the calculations. So first of all, I took the temperature of the bath, which you can see was 26 degrees C. That was from the video. Hopefully you saw that at the beginning. The uncertainty, 1 decimal place. It was just an analog thermometer, so plus or minus half a degree C. My uncertainty on that will be 0.5 over 26 times 100, which I make. So that's going to be 1.9. Let's call that 2% uncertainty on the temperature of the water bath. The atmospheric pressure in Singapore today, I googled it, put my hands up, and then I used Google as well to translate the 1010 millibars to 0.997 atmospheres. The volume of gas collected was about 102. You saw on the video I obviously had parallax error on the reading. I couldn't quite see underneath the surface of the liquid. It'd be better if you did this as a 2-person operation. That person can say stop now. I was doing it as 1 person, so it's approximately 102. It's at least plus or minus 1 cm cubed. 1 over 100 times 100 is about another 1%. The butane start mass was 0.01, that's over 11.28 times 100.01. I'm just calculating on my calculator at the same time. 11.28 equals times 100 equals 0. So we'll call that 0.1%. It's going to be roughly the same for this one, 0.1% there. And the total mass is then going to be 0.23, which is the difference between the start and the end mass here. So total uncertainty is for now 3.2% so far. Is all the gas in the measuring cylinder butane? Have a little think. No, it's not, because H2O liquid will be in equilibrium with H2O gas or vapor, the water vapor, and the water does have a vapor pressure. The vapor pressure at 25 degrees C was 25.2 torr. I don't claim to understand torr. Thankfully, Googled it again and translated it to atmospheres. To get the partial pressure of butane, we need to take the atmospheric pressure and take away the pressure that the water vapor here exerts in this experiment. The difference is 0.964, and that is going to be in atmospheres. Using P1V1 over T1 is P2V2 over T2. Just to emphasize, P2V2 over T2 here is at STP. Okay, so 1 atmosphere and 22.4 decimeters cubed or liters, 273 Kelvin. And you'll see when we substitute that into the equation here. So the P1 was 0.964, which is this one here. V1 is 100 cm cubed. I overshot, it was about 102 cm cubed. You're going to use 2 people and do better than me. 26 is going to be the degrees C, which was at the start of the video, plus 273, because this needs to be in Kelvin. Plug that into your calculator, 3.2 by 10 to the minus 4. That's for the P1V1 over T1 part of the equation. And then finally we need to over 1 times 273. I got the answer of 0.0874 dm cubed. Okay. Moving on, we need to use Avogadro's law. So V1 over M1 is V2 over N2. Substituting our values in. 1 mole, we're using 22.4 dm cubed at STP. I'm going to assume that butane behaves as an ideal gas. So 0.0874 over N for V1 over M1 is V2, again STP is 22, that should say 0.4, not divided by 4, but it's 22.4 over 1. I got N to be, which is N1, which is here, 0.0039 moles. We now know the moles, we know the mass. The mass was what we took, or the difference in mass between the start and end of the lighter. Divide that by the number of moles, and you'll get the molecular mass. I got an answer of 58.9 grams per mole. When I Googled again, today's video is brought to us by the power of Google, we found that the MR of butane is 58.12 G per mole. So if I take the difference between those two, the expected and the actual, then divide it by the actual, which is this one, I get a percent error of 1.4%, which, all things considered, we already had 3.2% error up here. I think we did rather well. Sources of error is my ineptitude at not asking a second person to help, but also the lighter has lots of water inside, which is very difficult to remove just by shaking and wiping with a paper towel. Okay, I hope you found that useful. Any questions, ask them below. Like, comment, subscribe. Thank you very much indeed for watching.